Hi everyone, let's get started with our today's lecture. Basically, lecture 22 will be focused on the introduction to statistics. We have been focusing on probabilities and we talk about a lot of content in it. And then, we already mentioned what is the difference between probability and statistics. We're going to talk a little bit more about those in this class, but primarily we're going to focusing on the statistics, and you can see that there are some differences, but mostly connections here. And before we get into more of the content, let's make sure we understand some of the key terminology which are listed here. So the first one is population, right? A population is a collection of all units of interest. And in this figure, you can see that each of this orange dot, each of these orange dots is one individual, right, or one unit, and then all of them, that's a population. That's a population, right? And then uh, the opposite of population is a sample, right? A sample is a subset of population that is actually observed. So we may not be able to observe all the population. Maybe you feel very strongly, and you probably can feel that very strongly with the current outbreak of the coronavirus, right? So we cannot test all the population. We can only test a small sample of population and see if they are infected or not. And like we're currently in a state of emergency, right? It's not because 2/3 of population have been infected. It's but because based on the observation, we see a lot of growth in the samples we tested, and we are afraid of the trend. That's why we entered into the state of emergency, right? That's the population, right? A parameter here, another term, a parameter is a numerical characteristic of a population. So when we talk about a parameter, we apply that to the entire population, right? Not just on individual. We apply it to the entire population. So whenever we say a parameter of something, we're talking about a population, right? And a statistic is a numerical characteristic of a sample, right? Contrary to parameter, when we say statistic, we're talking about the sample. It is used to infer the values of parameters, right? This is this is used to infer the values of parameter. So if we talk about in this figure, right, if we talk about the mean of all the population, that's a parameter, right? If we talk about the mean of the 3 people or 3 orange dots inside of this sample, that's a statistic, right? So we use the mean of the sample, which is statistic, to infer the mean of the population, which is a parameter. Right? That's what we're trying to do. A random sample gives an equal pre-assigned chance to every unit of the population to enter the sample, right? So we assume if we say this is a sample, this may not be a random sample. Maybe we observe. You can observe every. We want to understand the population, but like I said, I cannot go to my daughter's preschool and say, oh, there are 12 people. This is sample. I do the calculation of their age. The average is 4 years old. Then I assume the average of the entire United States, the average age of the entire United States population is 4, right? That's wrong because the sample I get, the sample I use is not a random sample. It's not an equally pre-assigned chance. Not everyone have an equally pre-assigned chance, right? So that's the difference here. Basically, a sample doesn't mean a random sample. It's more strict. There are more strict rules to follow to get a random sample. We assume the population and its parameters are unknown, and the sample is used to infer the value of the parameters. That's we use a sample. If we know everyone, if we know in the entire United States for the 350 million people, we know everyone if they are infected or not, there will not be a declare of state of emergency, right? We don't need to worry about it. We just need to quarantine all the individual who has been infected, then we're done, right? The challenge is that usually we cannot know the entire population. We can only refer to a few individuals, which are a sample, and then that's why we need statistics, right? That's why we need statistics. And you can see different samples give different estimates of population parameters, which is called sampling variability, right? Like I said, if I choose a population choose a preschool class to find the average age of the United States population, I choose a nursing home, I choose country club. They all give different number, right? So it's important to understand that this is variability. Because the sampling variability, it can lead to sampling error, but error doesn't mean it's wrong. Here, error just means how far we might be from the truth. As long as we can quantify and control the error, the sampling are still valid. It still gives us important information, right? That are something we're going to talk about in the class. So here, you saw this figure, well, these two figures many times before, but here are the differences. Probability is deductive, basically meaning that giving the information in the box, what is in your hand, right? Giving the information in the box, what is in your hand. But statistics is inductive, basically giving the information in your hand, what is in the box. That's quite different, right? Now, to emphasize what we talked before, right? Population leads to parameter. We use parameters to describe population, and we use statistics to describe a sample. Population is basically a group of all items of interest, and the parameter is descriptive measure of a population. Then the sample is part of the population, right? A small set of data drawn from the population, and we use the statistic to describe as the descriptive measures of a sample. Now those are the difference here. There are statistical methods to understand our samples, right? Some are descriptive in their nature. These are basically collecting and describing the data, relatively basic level, right? Then there's the inferential statistics, which you use to draw conclusions and are making decisions concerning a population based only on sample data, right? Here, obviously, we're making one step forward, right? We're trying to draw conclusions or even making decisions for one population based only on sample data, right? Again, back to the coronavirus example, we draw a sample, we know that there are 92 individuals in the United States, in the Massachusetts area are infected, they have the virus. Then based on that and based on historical trend and maybe trend in other countries, the Governor Baker draws a conclusion that we need to declare a state of emergency, right? And then based on that, probably based on similar information, the president of Northeastern University and Harvard University decided that, okay, the university need to be closed. And that's important, right? So that's basically how we draw conclusion and make decisions concerning a population based on a sample data. Now, a few more. I want to say some more about statistical inference, right? Statistical inference is a process by which we acquire information about populations from samples. It's a process by which we acquire information about population from samples, right? So, like in this case, we cannot test all the individuals. So we select 1, 2, 3, 4, 5, 6, 7 individuals and do certain tests. And then we try to draw conclusion for the entire population, right? The estimation, there are two ways to do this. One is estimation. Basically, it is used to determine the value of a population parameter on the basis of a sample statistic. Again, we use that to determine the value of population parameter on the basis of a sample statistic. This can be estimate the mean trip rate, the population mean trip rate based on the sample mean trip rate, right? Then there can also be a hypothesis testing, right? So somebody told me that, okay, on average, each individual in the United States make about 3.5 trips per day. That's your hypothesis. Then I'm going to gather some data from the sample and test, well, is this true or not? Right? Is this really true or is not true? Right? That's testing this hypothesis. There are quite a few similar concepts calculations we can do, or some of the parameters and statistics look almost identical, right? For example, here, the mean value. For population, we use mu to represent population mean. So basically, we add all the number together, divided by the n, which is number of population, capital N. That's the population size. And that's our mean, right? But we do basically the same for sample, right? Sample mean, we use X bar to represent. And you can see that we still, same thing, we add all of them together, every individual's value from the sample together, and divided by n, which is the sample size, right? This is lowercase n. We get the same result. Same thing, we can calculate the variance. We did this before, so I'm just doing a quick review. That for variance, which is the sigma square, for the entire population, that we use sigma square to represent that, right? And then basically we use each value minus the population mean, which is mu, do the square and add them all together, then divide by the population size, right? Same thing for sample. Well, a bit different for sample. We use S square to represent it, the variance of sample. We use each sample value minus the mean value of the sample, do the square. Then in this case, we divide n minus 1, right? The degree of freedom are different. We already talked about what are the differences. If you are a bit confused, definitely go back to our Microsoft Teams classroom and try to find the articles I shared before, right? But I mean, for here, just remember, for sample, we need to divide by the sample size minus 1. But for population, to calculate the variance, we need to divide the entire population sample, right? Population size, right? That's a difference part. For sample, for the we showed that how to calculate the covariance and correlation before for the population, right? For sample, it's pretty similar, but here you can see that all the part is the same, except here instead of divided by n, we divide by capital N, we divide by lowercase n minus 1, lowercase n minus 1, right? And then when we try to calculate the correlation coefficient, before we use rho to represent that. Here we use R, that equals to the covariance of x and y divided by the sample standard deviation, Sx and Sy, and then this is how we calculate. This is how we calculate. You can see the function looks pretty similar. There are some subtle differences. We need to make sure we understand and remember those, but the calculation is pretty similar. To estimate or to gain better understanding of the sample, we use point estimator. We use a point estimator. A point estimator here, the point estimator of a parameter theta is a single number that can be regarded as a reasonable value for theta, right? A point estimator can be obtained by selecting a suitable statistic and computing its value from the given sample data. So basically, we're trying to understand something from the population, and then we can't calculate the entire population, right? Then basically what we are trying to do is just get a sample and then compute the value from this sample and use that to infer or estimate the parameter theta for the entire population. So you can see here the we want to know this, right? We want to know for the entire population how many people has been infected by the disease. What is the average age? What is the average income? We want to know the variance. How big is the income inequality? We can't calculate everyone, right? What we are trying to do is that we use the sample statistics. We can ask 100 people. We can test 500 people to see who are infected and who are not, and then do the calculation here, right? So whatever we calculate here, we infer or we use that to estimate, okay, this probably will be pretty close to mu. This will be very similar to theta square, right? So that's what we are trying to do, use the point estimator. Well, come back to what we discussed before, right? Okay, you can do that for samples, but how do you ensure that what we estimate are right? Because there can certainly be the sampling, there can certainly have the sampling variability, right? One estimation from a sample may not be the same, and usually they're not the same from another sample, right? Then how do you decide which one is the correct one? In here, you can see that, from this population, we can draw this sample, or we can draw this sample, sample 1 and sample 2. And then we can estimate the mean value for both of these samples. obviously different sample will provide different estimation, and the sample statistics is become a random variable, right? So the distribution, in this case, the distribution of the sample statistics resulting from taking all possible samples of the same size. The distribution, I'll say that again, the distribution of a sample statistics results from taking all possible samples of the same size. I can pick this 5, I can pick this 5, I can pick this 5, calculate a mean, I can pick this 5, calculate a mean, I can pick this 5, calculate a mean, I can even pick this 5, calculate a mean, right? Picking different 5 will give me different mean, and then I can calculate them and then draw the distribution. You know, we take the mean as a random variable, and then we can draw the draw the distribution. Right? So the sampling distributions is really the calculating parameter of, because we need that because calculating parameters of populations is prohibitive because populations can be very, very large, right? That's why instead of investigating the whole population, we take a sample, calculate a statistic related to the parameter of interest, and make an inference. So we can calculate all of this statistics. The sample distribution of the statistic is used to evaluate how close is the statistic to the parameter of interest, right? We use that to estimate how close is the statistic to the parameter of interest. That's what about sampling distributions. And then random samples, we already said this, right? The probability distribution of any particular statistic depends on the population distribution. It can be normal distribution or uniform distribution or exponential distribution, all the things we talked before related to the sample size, right? You want to understand 350 million people, but you only get 5 people to do the estimation. Of course, the error could be larger, right? If you can get 1 million people, then it will be much narrower, right? That's the important part of it. And then it also depends on method of sampling, right? That's why random sample is so important. We want to make sure that each individual have a chance to enter into our pool, so we can do the good sampling. Let's look at one example, and hopefully this will make more sense. The example here is sampling distribution of the mean, right? So the population is that households in an area, maybe in Boston area, right? All the households in the Boston area. And what we are trying to find is the number of trips per day per household in a population has the following distribution. In the population of following distribution. So assuming this is the assuming that this is for the entire population, right? So we find that 1/6 of all the population or all the household make 1 trip. 1/6 make 2 trips. 1/6 makes 3 trips, and then same 1/6 make 4 trips, 5 trips, and 6 trips, right? All like that, and they all have equal distributions, equal chance of making the same number of same number of trips, The chances are all the same from 1 to 6. And apparently there are no people stay at home at 24/7, and then there's no people making more than 6 trips beyond that. Let's assume that's what is happening, right? So based on this, we can calculate the mean value and the variance, right? Based on this, we can calculate the mean value and the variance. And certainly the mean is this, which is the 1 multiplied by 1/6 plus 2 multiplied by 1/6 plus 3 multiplied by 1/6 plus all the way to 6 multiplied by 1/6, and you can find out that the expected value is 3.5. Very straightforward, right? After we have the expected value, we can easily calculate the variance for the entire population, which is 1 minus 3.5 square multiplied by 1/6 plus 2 minus 3.5 square multiplied by 1/6, so on and so forth. That give us 2.92. That's the variance, right? Okay, we know that. Suppose we don't know all of them. Right? Suppose we want to estimate the population mean mu from mean x bar of the sample of size n only equal to 2 households. Assume that we can only observe 2 households, and we can calculate the mean, right? Then how can we estimate the population mean mu from the mean of x, right? How many different samples are there? And what is distribution of x? What is distribution of x bar, right? I'll give you, please pause the video and take a few minutes to think about it. See what do you think will be the samples, and what is the distribution of x bar? All right, so how many different samples we can draw? That's pretty easy, right? This is the result. So basically there are 36 combinations. There are 36 of different samples, right? It can be 1 here, meaning that the first house, we only observing 2 households, right? The first one made 1 trip. The second one made 1 trip as well. Then it can be 1, 2, meaning that the first trip made 1 trip. The first household made 1 trip, and the second household made 1 trip as well. It can be 1, 3, meaning the first household made 1 trip, and the second one made 3 trips. So on and so forth, so on and so forth. So it's all the way to 6, 6, right? Meaning that the first household made 6 trips as well as the second household. For each of these, we can calculate the mean. In this case, 1. In this case, 1.5. Case 2, 2.5. 3, 3.5. In this case, we come up another 1.5, right? And another 2, another 2.5, another 3, 3.5, a new number, which is 4, and then continue, so on and so forth. The smallest mean is, of course, 1, right? And the biggest mean is, of course, 6. So that's the different sample size. There are 36 samples we can draw, and then the result of the means can be calculated, right? Based on this, we can find out the distribution, right? Based on this, we can find out the distribution because, in this table, we know how many times 1 shows up, how many times 1.5 shows up, how many times 2 shows up, and then we can just move them here into the bar chart, right? We can move them into the bar chart. We can see that again, right? The animation will show you again. So there's only one sample has a mean value as 1, right? So we put it here, right? This is households for the mean value equals to 1 trip per day. And out of the 36 sample, there's only 1 of that. Then out of the 36 samples, there are 2 have 1.5, meaning that on average, the household made 1.5 trips. That there's only 2 of those cases, 2 of this possibility. And then, but the biggest one is 3.5, right? Among this, we can calculate that 6 out of the 36 samples made 3.5 trips, right? For each value, we put them here and draw the distribution. Based on that, we can calculate the expected value and the standard deviation of the sample mean, right? Of the sample mean. How do we do that? For each value, we multiply by its chance, right? Add them together. That's our expected value. So for expected value, 1, there's only one out of the there's only one case of 1, right? Its chance is 1 over 36, right? 1/36. So 1 multiplied by 1/36, and then there's 2 over 36 multiplied by 1.5, and then plus 2 multiplied by 3 over 36, and then 2.5 multiplied by 4 over 36. So on and so forth, so on and so forth. We can calculate. And notice that the mean value is the same, right? Mean value is the same as what we calculated before, but the variance is different. How do we calculate the variance of the sample? 1 minus a number, take the square, multiply the probability, right? 1.5 minus a number, take a square, multiply probability. So on and so forth, you get 1.46. You get 1.46. Notice before, for the entire population, right, the variance was 2.92. The variance was 2.92. But here, when n equals to 2, the variance we calculated here is 1.46. Is 1.46, right? This shows that the mean value of the sample equals to mean value of the entire population. Yet, the variance of the sample equals to the variance of the entire population divided by n. Remember, before is 2.92, which if you use that 2.92 divided by 2, which is the number of household or sample we used here, that gives us 1.46. 1.46. So based on that, we know that the distribution of the sample mean, we get some properties, right? The mean of the sample mean distribution, the expected value of the sample equals to mu, which is 2 population mean, But the variance of the sample mean distribution here equals to the population variance of variable x divided by n, which is the sample size, So you see that this is our the probability. This obvious looks like normal distribution, right? Looks like more of normal distribution. We can do this for different populations, right? Different sample size. So for population, mu x equals to 3.5, and then the variance equals 2.917. That's for the population. If the sample size we take n equals to 5, that is our result, right? Mu equals to 3.5, variance equals to 0.5833, which is 2.917 divided by 5, right? And here's the distribution. If we take it to 10, n equals to 10, mu don't change, right? But the variance of the sample keep shrinking, becomes something like this. Variance becomes something like this. And the variance, apparently, you can see here, equals to 0.29, much smaller. Variance is much smaller. When the variance is much smaller, means the standard deviation much smaller. And then we put them on the same scale. You can see it's the same scale, right? Same scale. The shape of the normal distribution become linear, right? Become linear. And same thing, if we keep increasing n, mu still don't change, but variance become even smaller, only 0.12 something, right? And then we get even linear distribution, even linear normal distribution. So the standard deviation becomes smaller and smaller, right? And which makes sense. Standard deviation shows how different our data could be, right? How dispersed our data could be. If we take more sample, we have more confidence, and the dispersed become more close to what we're going to observe, right? So to sum up, right, the distribution of the sample mean, which is basically the sample mean x bar for a sample of size n from population following a normal distribution with mean mu and a standard deviation gamma is normally distributed with mean and variance. So basically the expected value of x equals to the population mean, but the variance of the sample equals to the variance of the entire population divided by n, right? This actually leads to the central limit theorem, central limit theorem. The sample mean, which basically states like this. The sample mean x for a sample from a general population with mean mu and a standard deviation gamma is also approximately normally distributed. Pay attention here. Normally distributed for sufficiently large sample size n. This needs to be a relatively large sample size n. And the mean and variance are this, right? It's interesting, right? Remember here we are saying that the sample mean is actually normal distributed. The sample mean x bar is actually normally distributed, follows a normal distribution. Remember here the result, what we observe here, right? This looks pretty much like a normal distribution, so that's right. But if you look at our original data, This is not a normal distribution at all, right? Normal distribution, you have a bell, you have a curve. But here, the probability for all the 6 cases are exactly the same. You can say it's a uniform distribution, although it's discrete random variable, right? But they're uniform. All the probability are the same. However, it doesn't really matter. Basically, the theorem is saying it really doesn't matter what the original distribution is, right? When you draw it from a sample which is large enough, sufficient large sample size n, it becomes follow normal distribution. It's become to follow normal distribution, right? So that is really interesting. And we basically can treat it as a normal distribution. Here we shows the different shows the different scenario, right? For a population distribution is something like this. If we choose n equals to 4, this is what it looks like. We choose n equals to 10, this is what it looks like right here, right? But even if the population distribution does not follow normal distribution, you can see it's tilted to the left, skewed to the left, right? But when we start to moving n larger and larger, picking a large enough n, it's become very much like a normal distribution. You see, it's approximately normal distribution. So it really doesn't matter what is your original distribution is. When you start taking the samples, it becomes more and more like a normal distribution. Right? You can treat it as a normal distribution. Of course, when we talk about large enough, what do you mean by large enough? What is large enough here? Right? The rule of thumb basically is if the underlying distribution is close to a normal density curve, then the approximation will be good even for small n. Whereas if it is far from being normal, then a large n will be required, right? Large n will be required. If the original distribution is more and more far from normal, then we need a larger n, right? The central limit theorem can be used in general if n is bigger than 30. If n is bigger than 30. Related to this, there's also the standard error of an estimator is its standard deviation. A standard deviation is basically the variance of certain parameter. We take the root and give us the standard deviation. Give us a standard deviation, right? So here, we take one example. The number of trips per household in a population is normally distributed with a mean of 32.2 trips per week and a standard deviation of 0.3 trips. And then what is the probability that a randomly selected household performs more than 32 trips per week? What is probability of that, right? Oh, well, the mean is 32.2, right? And the standard deviation is 0.3. Now, basically, we want to calculate what is the probability that a randomly selected household performs more than 32 trips per week. More than 32 trips per week. Here, the random variable x is the number of trips per week, right? X is the number of trips per week. For the population, we know that the we know it follows a normal distribution, and then we, of course, this is not a standard normal distribution, right? Then we basically, the first step is converting that to a standard normal distribution. So what we do is that we use we are trying to find a px equal to 32, right? Bigger to 32, sorry. Then to convert to a standard normal distribution, we use x minus mu divided by the sigma x. We need that to be bigger than 32 minus 32.2 divided by 0.3. So minus the the mean value and divided by the standard deviation. That after we do the transfer, it become z needs to be bigger than negative 0.67. And then we can use whatever calculation, and then we can find that the probability is equals to 0.7486, right? That's our probability. And from here, you can roughly see that, right? This is mean. This is the standard deviation. 32.2 is the mean. 32 is here. And this area is bigger than half, right? Bigger than the right half of the distribution. So that gives us, doing the calculation, we find out it's 0.74 or 75, which is bigger than 0.5. So as for the population, then what about, this is not for the population. What is probability that a sample of 4 households will have a mean of more than 32 trips per week? What is that? What is that possibility? Right? If we define the random variable as a mean number of trips per week, then basically what we are trying to do is we still do the conversion, but before we were doing on the entire population. Now we're doing on the sample, right? We're doing on the sample. Remember, for a sample, the mean is the same. Whatever mean for the population, that's 32.2, that's still the mean value for our sample. That stays the same, right? So that's why we still use 32 minus 32.2. That's how we convert this part. But for this part, we need to divide it by the sample standard deviation. For sample standard deviation, we cannot use 0.3 anymore, right? Because sample standard deviation is this, or the variance is this, right? To take the root of that, that gives us the sample, the sample standard deviation. So basically here, we need to find out what is the variance of the sample, which is 0.3 square divided by 4, which is the sample number, right? Which is the sample size, and then take the root. That's basically how we get this number. Why we are dividing by 0.3 instead of why here we are dividing by 0.3 divided by root of 4, so basically 2, instead of directly divided by 0.3, because we need to use the sample variance. So that gives us 0.15, right? 0.15. Doing the calculation, we find that here we need to find for standard normal distribution, the z needs to be bigger than 1.33. Then go back to our table, we can find out the result, which is 0.9082. That's our probability, right? That's our probability. And you can see that the two distributions are very much different. The two distributions are very much different. They are both normally distributed. Their mean are the same, but you can see that in here, the number, the mu, the standard deviation are quite different. The variance are quite different. The standard deviation are quite different. And of course, that's why the probability we calculated here are quite different as well. For the sample, the normal distribution are much more thinner, right? Much more concentrated. So that's how we estimate certain numbers, errors for the sampling, for a sample. There are some estimators properties I hope you can remember. First one is that selecting the right statistic to estimate a parameter value depends on the characteristics of the statistic, right? Depends on the characteristic of the statistics. We showed how the mu, or the mean value or expected value, and the variance are same and different. And then you can see that it depends on what you are trying to estimate. The value are quite different, right? How do we do the estimation are quite different. For one estimator, the desired property is always unbiasedness. An unbiased estimator is one whose expected value is equal to the parameter it estimates, no matter its mu, no matter its variance, no matter its standard deviation, or this can be median, this can be mode, this can be 50 percentile, 75 percentile, all those, right? We want it to be unbiased. We want it to be unbiased. Now that basically means, right, whatever we estimate of a theta is quite similar to the theta hat, right? We want them to be the same. The theta to be the expected value of theta hat. But if the red curve, the white curve is the unbiased case, they're the same. So, but if in certain cases our sample are biased, either we only draw population from preschool, we only draw population from poor neighborhood, or in certain cases advantaged neighborhood, that can give us very biased result, right? So we want it to be unbiased, and the point how to estimate is basically a point estimator is said to be unbiased estimator if these two are the same. And that's the point estimator. That's all I want to discuss in this class, and I'll talk to you next time. Remember, from now on, all the classes move online, and but none of the other things going to change. None of the other plan going to change. Please always use the Microsoft Teams Classroom to submit your homework, and see you again very soon. Bye.